Disseminate, the Computer Science Research Podcast.
Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. We're back with today with another cutting edge episode, and we're going to be talking about fast and scalable data transfer across data systems with Harry Gavrilidis. And Harry is, 3 times now you've been on the podcast, Harry, right? So welcome back for the 3rd time. I'm really glad to have you back on the show again to tell us about your latest research, which is due to be published at SIGMOD this year, right? So welcome to the show again, Harry.
Yeah, thanks for having me again. I hope you can cope with me the 3rd time.
Cool. Yeah, quick plug as well for Harry's other episodes. We've got In Situ Cross Database Query Processing, which was episode 27. Go check that out. And he's also got an episode where we talk about his work on Sheet Reader in the context of the DuckDB research series, which hasn't actually been released yet. So depending on when you listen to this podcast, it may be out, it may not be out, but it'll be hopefully out and in your feed somewhere. So go do check that out, listener. 2 really good podcast episodes, that's for sure. So let's get on to the topic at hand today then, and Harry. But before we do that, the usual, tell us about your story. How did you kind of get interested in database management? And tell us about your journey to where you are today.
Yeah, so overall, my journey into database systems started when I did my bachelor's at TU Berlin. And back in the day, the lab was developing Apache Flink. I mean, I guess it has become a big success story. But I joined the lab when the Apache Flink story was fading out and new things were starting to happen. And I did my bachelor thesis back then. At the lab, and then I thought, data management looks pretty cool. So I went on and did a master's there as well. And the one thing led to the other, and here I am now, hopefully soon finishing the PhD. And I'm looking forward to talk to you today about the data transfer topic. That's one of the it's the last topic of the PhD, actually.
Nice. Last and best?
Yeah. I mean, you know how it goes when you advance in the PhD. You get more experience. So
This is true. Yeah, for sure. Well, I read it and it was a very interesting read. So I'm sure the listeners are going to like what we've got to say about it today as well. So cool. Going off that then, let's set a bit more context for this chat and about talking about data transfer. So tell us about what data transfer looks like in the modern environment, in the modern data ecosystem, and tell us why it's important and what are the various challenges with it today.
Right. So this work also originated. I mean, it's related also to the XDB system, where we were dealing with federated query processing, and overall, we see that there are many use cases around where you have to transfer data from one system to the other, right? You have the typical ETL use cases where, data flows through systems, gets transformed and prepared for downstream tasks or like for storage in a data warehouse. You have federated query processing where you need to combine multiple data systems together to answer analytics queries. You have, IoT use cases where you have also different nodes communicating with one another, and they also transfer data. Overall, data transfer is crucial for data systems interoperability. So when you have multiple systems working together, or when you need to load your data, as one would say, from one system into the other. This is a crucial task. And what we realized when we were doing the XDB work is that large portion of the query processing time went actually to data transfer. So data transfer involves many operations, and these are expensive. And in this work, we try to see how to mitigate this. One other aspect is that data transfer occurs in many different environments, right? So you may have your systems on the cloud. So when both systems are in the same cloud and there is a high-speed network between them, and the nodes are super powerful. You might have two systems that are located on different clouds, so the network between them is not the best. Then you might have data scientists working on their laptops with like a normal internet connection connected to the cloud. You may have IoT nodes that are, let's say, less powerful. And overall, we have different environments where data transfer occurs. And then related to, you asked about, state of the art for data transfer. And this is, so I categorize data transfer approaches in two main categories. So on the one hand, we have what I call generic data transfer methods. And there you would have something like JDBC, right? So there you just plug and play your driver and you can talk to any system, and that's super fine because, it's generic. So it allows you talking to many systems. But on the other hand, this is not, very well performing. And there was also a paper some time ago from CWI, actually the DuckDB folks, and they showed that, the JDBC protocols are actually not that good. And so that's the one category, the generic data transfer. And then we also have what I call specialized data transfer techniques. And there we have, let's say, these point-to-point connectors where I can implement very efficient connectors between pairs of systems. And of course, the advantage there is that I can squeeze out performance, and it can be the best the best achievable performance. But this means that I also have to implement for every pair of systems a new connector, right? And with this work, XDBC, we want to strike the balance between both worlds. So we want to be generic, and we also want to be efficient.
Nice. Yeah, just the first comment there, what I'm going to make off of the back of that is it's really nice to see how one piece of research has sort of led to another with your work on XDB. Has kind of lit the light bulb and kind of gone, oh, hang on a minute, well, this is a problem, we can do this. So it's nice to see how, like, it's a good example of, like, how our research can be iterative, and by the act of doing things sort of unearths new things and new directions. So that's really cool to see. But yeah, I'm kind of getting from you there that data transfer, a lot of heterogeneity across these systems, and it's difficult to sort of have this movement of data between these systems. Is a lot of that, do you think, maybe a function of systems don't make it easy to let go of their data because they kind of want to lock their data, the data in? There's kind of a business use case for making it sticky, right, to get your data out because you don't want your customers to go away, right? So I don't know whether that sort of plays into it at all as well. Yeah, so
that's a very good point. Also, we have seen that the emergence of Apache Arrow, right? So this in columnar, in memory data format or representation. And the idea there is to standardize formats across systems, which is nice also as an interchange format because of its binary representation and the compact format and the nice integrations. But then, as you said, all systems internally most of the time use their own format. And yes, on the one hand, I think you're right. It's because of, the business case, and you want your data and your customers caged in your system. But on the other hand, I think it's also because of, system specific optimizations, let's say. So each system is optimized for a different use case. And they may benefit on the processing side from their own internal format. Right. And of course, in a perfect world, everyone would have something like Apache Arrow internally, and then you could just change transfer your data using Apache Arrow everywhere, and you wouldn't need to transform it. But I think we're still far away from that.
Yeah, cool. So just to recap quickly there as well, the kind of, I guess, the current state of the art is you have these generic sort of approaches like the JDBC, which is kind of good. It's generalized. You can kind of plug and play and put these things together, but pretty much bad performance, doesn't really sort of, perform well. And then on the other end of the spectrum, you've got these really specialized things, sort of these between two, system A and system B, and sort of can do between this pair of systems really fast and really efficiently, but then that doesn't generalize. So XDBC is going to sort of solve this problem for us and give us a nice sort of generalizable framework, but also something that is not sacrificing performance for this as well. So yeah, let's talk about the architecture of XDBC then, and what does this system that's going to give us these nice properties actually look like?
Yeah. So we looked at the data transfer pipeline, right? So and so because we want to be generic, so let's focus on the generic part here. So for example, in JDBC or in other similar or ODBC or like also in the Python ecosystem, SQL Alchemy, or you name it, connectors, you have like a single, you have a very tightly coupled pipeline, right? There are many steps involved in data transfer. So you have to read your data from the source. You need to deserialize it into an intermediate format. You need to maybe compress it. You need to send it over the network. And then on the other side, you do the reverse, right? And what we observed is that there is little configuration opportunity there, or like optimization. So there are very few parameters that you can set. And also that all these steps are kind of tightly coupled together. So the main idea of XDBC is to first to decompose this pipeline, and then to be able to individually configure all these different steps of the pipeline to achieve best performance in all environments, right? So the architecture, you can imagine it as like different components that are interconnected with queues, and they are individually configurable and scalable, let's say, in terms of parallelism. And when you want to add a new system, you implement only like few of those components. Like we have some interfaces, and for example, to add a new source, you would implement a reader and a deserializer, and then you can join the party and let's say act as a source for all the different systems that already are part of the XDBC framework.
Nice, cool. So we've got these reader writer interfaces, and then the general idea is sort of decompose this pipeline into decompose all these the process into these different. So let me start again. Decompose this whole process of moving data into these different logical sort of steps, the components of the read, deserialize, compress, send, receive, decompress, serialize, and then write again. Cool. So maybe it'd be cool for the listener if we sort of went through the life cycle or the flow of a actual request of like, hey, all of a sudden I want to get some data from system A to system B. How does that look like with XDBC? What's the flow of requests, and how does that all piece together?
Right. So, the flow you already mentioned. So let's have an example. Actually, let's say we want to load a table from a database into a Pandas DataFrame, right? I think this is also the example that we have in the paper. So the idea there is that to now load the Pandas DataFrame from the database table, you would initiate the transfer, and so on this on the Pandas side, we have the client, the XDBC client, right? So XDBC consists of a server that sits next to our source system, and the client that sits next to the target system. And the request of the framework that wants to load the data goes through the client, and then the client communicates with the server with which data you want to have transferred, and then the server actually initiates the reader. And the reader starts pulling data from the source system, and then these data are organized in buffers, right? So we fill those buffers. The buffers get into our system from the reader to the deserializer. Their deserialization happens to some intermediate formats. So we support different intermediate formats. Then you go to the compressor. Data gets compressed. You send the data over the network. It gets into the client. There we may decompress the data if it's compressed. Then we serialize it into the target format. and finally, we load it into the in this case into the Pandas data frame. And so as I said, there are these many different steps involved, and now let's say the data frame, the Pandas environment runs in a laptop, right? So this means that maybe we don't have so much memory available, or we don't have so many cores available. So the cool part here is that we can configure different amount of threads for all the different components, right? So and we have seen in the experiments that, for example, when over provisioning, this leads to worse performance. So you have to actually find out the best parameter configuration, and this is part of the optimizer that I will come to later. But also, for example, if now the laptop is in somewhere with a normal internet connection, we would probably enable compression. But then, for example, if you use some service like Google Colab or something that sits in the cloud next to your database, you would probably not enable compression. So this is the cool part. So you can configure all those different steps individually in different environments and adapt the parameters in such a way that you get the best performance possible.
Yeah, really like it, kind of the granularity you have there over each component, how you can kind of change it to suit the heterogeneous environment that you happen to find yourself in, right? Feels great. I have a question on the so when we're setting up does the client spawn the server process, or do you have to manually set up both of these processes next to or in their own where do you do you always co-locate them with the source and the target system, or can they be standalone? And do you have to stand those two things up before you then can send the client can send the request to the server, right?
Right. Very, very good question. Yeah. So this is up to the implementation.
Okay.
But we have both. So for example, when you want to load data from a Postgres database, so right now we have like a standalone XDBC server that actually sits next to the Postgres instance, right? But we have also done some work recently where we try to integrate it as an extension into Postgres, right? So that you can actually just hit the Postgres database without any service running next to it.
Nice.
And then for the clients, it's a bit different when, for example, we have an Apache Spark source, and there we just use the data source API. It's just another source in the system, so that we have XDBC is like a shared library. So the main functionality is packaged as a shared library, and then you kind of need to integrate it into your framework. So, for example, in when we want to load data into Postgres, we use a foreign data wrapper that allows you to read data from external sources. Then, for example, for Apache Spark, we use the data source API, as I mentioned, and there we wrap the shared library with JNI because XDBC is implemented in C++, and so you need the bridge between JVM and native code. And then for Pandas, we use we also use the CPython integration where you can or PyBind, where you can also integrate native code with Python code.
Nice, cool. Yeah, kind of going off the components, and there are a few other sort of ingredients in the runtime of XDBC that kind of hold everything together. You touched on the memory management a second ago, but if you want to go into that a bit more, then please do. But there are other aspects of it around parallelism and backpressure. Maybe you can tell us about those runtime components as well.
Mm-hmm. Yeah, so as I mentioned, we have these different components that communicate through queues, and the memory is also configurable. And by memory, I mean the memory that you want your server to use or your client to use. For example, if you're on the cloud, you may have available a lot of memory, but if you're on a resource-constrained device, you might not want to use a lot of memory. And in our experiments, we actually also saw that with very little memory in the order of megabytes, you can also efficiently transfer gigabytes of data. So we have a memory pool, and we divide it into logical buffers. And then, so the pipeline, starts at the reader. So at the server side, right? And, we actually get the foreign data that sits, in our example, for example, in Postgres, and we, read it, into our, buffer. So then we have, Postgres, data in our buffers. And, then we, place the, so we then need to send it to the deserializer, right? But we actually don't send the whole buffers. We just send pointers to the data, and the components communicate through queues. So we actually enqueue if you want the buffer IDs, and all the queues also have like a maximum capacity, right? So so we enqueue the elements, the buffer IDs into the queues. And this way, all the different threads of one component can actually, whenever they are done, they get an element from their input queue, do the work, and send it to the next component. And this means that a component can at one time occupy like a thread 2 buffers. So the one that it gets from the upstream task, and then you get a free one. You do the work, you put it in there, and you send it to the downstream component. And now, of course, in a queuing system like this, the throughput is bound by the slowest component. And by setting this maximum capacity at the queues, we ensure that the backpressure is handled. So whenever some component is a bottleneck, it will backpropagate, and through these constraints of the queues, we will not overflow the system. So in the end, the reader will just stop reading new buffers and putting them into the system.
Nice. You have this inherent backpressure, which is really nice, right? Because you don't want these things overflowing. Cool. Yeah. So we've been talking about the components in sort of the abstract sense of sort of serialize, deserialize, etc. Let's talk about the actual physical implementations you have of those, sort of, I guess, thinking about them in terms of database and like operators almost in a way, right? So yeah, tell us about the physical implementations that you have of the various components in this pipeline.
Yeah, right. As you mentioned, so in a sense, in a way, the architecture is like a data flow system, right? So we have logical components that we have talked about, the read, deserialize, etc. And we then have some physical implementations of them. So, for example, the reader and deserializer physical implementations are up to the developers who want to connect their system. So, for example, you could have a physical reader would be just reading data from a Postgres database, or from a CSV file, or from a ClickHouse database, or whatever system you want. And then the deserializer. So here we need to transform the data from the source format into an intermediate format, right? And here we have we can choose the intermediate format, right? And we provide our own row format. Row and columnar formats, right? This is, columnar Pax-like, right? So essentially, this is like Arrow, where we organize the data in record batches, if I would use the Arrow terminology, right? And so you can also bring your own intermediate format. So this means you would then implement a new deserializer that takes Postgres data, for example, or whatever data you have, and will serialize it into a different intermediate format. Then we have the different compressors. So right now we have some standard support for some standard compression libraries. So the physical implementations would be for we have ZSTD, LZ4, LZO, and Snappy. But because we operate on a buffer at a time, you can very easily just bring your own compression algorithm and plug it in as a physical operator, a physical compression operator. And then for the network, right now we use TCP transfers. So right now we leverage Boost ASIO, the Boost ASIO library for networking. But again, like if you want, you can bring your own RDMA library or UDP or whatever. So then you would need to implement pairs of senders and receivers. And then on the other side, it's just the reverse, right? So you would need the decompressor. I mean, this goes again hand in hand with the compressors, and on the other hand, the serializer and the writers, these are also system specific.
Nice, cool. So given that we've got this smorgasbord of various components and everything, the really interesting part, I think, is the really appealing part of this whole thing is the optimization, how to pick, given a certain environment and systems and whatnot, what is the best setup to use. So yeah, tell us about the optimization algorithm you have to sort of pick all these different components, these different operators, and piece them all together to be the most efficient.
Yeah. So yeah, up to now we talked about the general transfer framework, right? And that we now have all those nice options to configure. So we can configure the different threads of the component. We can pick different intermediate formats. We can pick different buffer sizes. We can pick different compression algorithms. And of course, as you said, I mean, we can configure it now, but who knows what to pick in each environment, right? And to show the impact of different configurations, we ran some experiments where we I think we just varied the amount of threads, and we simulated different environments, and we just varied the amount of threads that we use, and we saw that actually there might be an order of magnitude performance difference. So if you pick a very bad configuration instead of a just okay one, you are very off, and you don't want this to happen. So how do we go about this? We to solve this, we have an optimizer. So the optimizer gets as an input what we call the base throughput rates of each component, right? So this we obtain through profiling. So you can imagine either you do like one run in the beginning, or this can even be one can obtain this information also on the fly, like just in the beginning of a transfer. So you want to know each component, how fast each component processes a buffer. And given this information, now we have our, let's say, base throughputs, and we also have an amount of threads that we can give to our server and client. So overall, right? So the optimizer is pretty straightforward in that sense that so we go to the slowest component, and we just keep adding threads until it's not the slowest anymore. So we do this in an iterative fashion until we run out of threads. So for example, we start and we see that the deserializer is the slowest component. So we just add threads to it, and we estimate the throughput that it would get with different amount of threads using Gustafson's law. So of course you don't have linear scalability when you just add threads to a task, right? So I mean, there is some estimation work there, but the idea is that we go to the slowest component. For example, the deserializer, we say, okay, with one thread you achieve X throughput. Now take 2 threads, and now we reevaluate and we see, okay, now the network is the bottleneck. Okay, now let's add compression. Let's say, okay, now we have compression. Can we do faster? And what I forgot to say is that we also have some bounds, right? For example, you have your network limit. So you cannot, even if you try very hard, you cannot be faster than the network, right? So yeah, we optimize our threads until we either we optimize the amount of workers for each component until we run out of available threads, or we have reached the upper limit, let's say. Yeah.
Nice. Yeah. Sorry. Sorry. Continue, and then I'll jump.
Oh, I just wanted to say that also. Then we might talk about this later as well, but in the evaluation, we saw that also depending on the data set, different compression libraries work differently, or depending on the available amount of threads that you have in your system, you may want to use different compression libraries. So we saw that it actually makes sense to configure these components individually.
Nice. Yeah, I was just gonna say, eventually you reach the bounds of the laws of physics, right? Essentially, so you can't go any faster. It's physically impossible to. But yeah, I mean, on this, how quickly can you converge to? Maybe I'm getting into the evaluation, but how quickly do you converge to the optimal strategy of the transfer? Like, if it's a really short transfer, I guess it might take time to sort of reach the optimal setup. So is there sort of, I guess, a size of transfer before it, like, we'll maybe get into the evaluation, but then my other sort of sub question to that was like, is there memory over time of being like, oh, this transfer looks similar to this one I did before on this same, like, sort of hardware environment, therefore I can jump to nearer the optimal quicker?
Yeah, very good question. So in the first version of XDBC, I mean, this is already a couple of months old, but it's an ongoing project. But in the first version, we would, just have a profile for a particular data transfer for a particular environment, and the heuristic optimizer would output, one configuration, and this would be it. So of course, when you would run the transfer again, you would get your new profiles and adjust. But this we didn't explore so much.
Sure.
Now we have an ongoing project where we actually try to learn, let's say, from past transfers, or we try to build. It's very cool work actually. But yeah, I don't have the full results yet. But the idea there is that we can categorize different environments, and we can sample some configurations. So that we see which configurations run well in different environments, so that we have a good starting point. So because, I mean, we do all this micro benchmarks, and the idea is to build a model that we can already embed into the connector, so that it has a good starting point on the one hand, so that if you identify in which environment you already go with a good transfer. But it also will learn on the fly.
Yeah.
And
nice.
We have seen that, so after a couple of iterations, you already converge close enough to the best possible throughput. But this is not part of the original paper. Yeah.
No, sure. Yeah. And also, I guess, following on from that, the big acronym in the that's lurking in the background, AI and machine learning. When are we going to get an ML based optimizer for XDBC? I guess we're kind of getting there. We're back, and it's going to learn over time. So it's getting into that sort of thing. But yeah, I guess there's a whole host of techniques from sort of maybe the ML based sort of query optimization and all that sort of stuff. Techniques that can maybe be applied to this setting as well, maybe.
Yeah. So, I mean, I don't want to spoil, but this is ongoing work. And actually, we have applied some ML techniques, but also more traditional optimization techniques.
Yeah.
And to be honest, traditional optimization techniques also don't perform that badly. Yeah,
that's kind of consistent with some other research I've seen before, and people I've spoke to around. A lot of the time that these traditional, less fancy techniques can get you like 80% of the way there, or good enough 90% of the time, or whatever. Which is, there's that complexity, understandability trade-off, right, as well. And so that's interesting that may apply to this setting as well. What's it like from? I mean, obviously this being a research project, but from like the user experience, what is the tooling around like monitoring how things are happening? Can I visualize how long my transfer might take given the way things are at the moment? Like, is that sort of information exposed in any way?
Yeah. So we have like because in Now, this is also not part of the original work, but this is ongoing work. Things move fast.
Yeah.
So here we also want to be able to change the parameters during runtime, right? So in the first version, I said we have the heuristic optimizer. We give it one configuration. The transfer runs, and then maybe in the next transfer you can re-optimize. But what we're working on now is actually dynamic reconfiguration, so that during runtime you can scale the different amount of threads for each component and stuff like that. And therefore we expose because the optimizer actually needs this information. I mean, you maybe also, as you mentioned, as a user might also want to see why or what is the bottleneck of your current data transfer. But this is also important for the optimizer, right? So it needs to get this information to take better decisions. So yeah, we have like an endpoint where you can both set the different parameters, but also get the current runtime information. Yeah.
Nice. That's really cool. Let's talk about some numbers and an evaluation and put some numbers to this discussion. So yeah, first of all, set us up. What was the experimental setup like? What were the benchmarks you ran? And yeah, tell us the results.
Yeah. So first we wanted to see like end to end. Right. We have different state-of-the-art tools for transferring data, and can we reach the performance of specialized connectors, right? And do we also outperform the generic solutions out there? So this was our goal, and to also have different environments. We used a setup with Docker, and Docker has some really nice properties where you can set the amount of the amount of CPUs that you want the container to have, and you can also change the network characteristics, like with Docker. I mean, it's a TC like utility. So this is the setup. So we spawn our systems in Docker containers. We configure different CPU and network characteristics, and yeah, we run our benchmarks. And as I said, we wanted to first see end to end. How does the performance look like? And therefore, we picked different use cases. For example, from the data science domain, one would want to load the Postgres table into a Pandas data frame. And here we also tried out different data sets. And an important baseline here was ConnectorX. This is also a recent VLDB paper. And we have this as a specialized connector because this one is really optimized for transferring your database tables into Pandas data frames. And there we saw that we are actually on par with ConnectorX. Sometimes little bit faster, sometimes a little bit slower, but overall we're in the same ballpark. Then we also have DuckDB as because it has a specialized let's say Postgres reader or like database readers, but in this case we use the Postgres reader, and here we are I would say around 3 to 4 times faster when loading a Postgres table into a data frame. And then we also use these generic connectors, like Modin has one which also can parallelize, and then we also have the Turbo DBC connector, and there we actually are, I mean, it's around maybe 10 times faster. But again, these are generic connectors, right? So this is expected behavior. Then maybe I can also talk a bit about the when we want to transfer a Postgres table to Spark, right? So here we also use the standard JDBC driver of Postgres in Spark, and here we also see this is like also something like for the line item data set, for example, that I see here is around 5 times XDBC is 5 times faster than the default JDBC connection. Then I also have another interesting experiment where we transfer Postgres table to a Postgres table. So here we also have as baselines JDBC. So Postgres allows you to have these nice foreign data wrappers, right? And we talked about this also in the XDB podcast. So the idea there is that you can actually access data that's not inside your Postgres database, but living somewhere else. And one way to implement a foreign data wrapper is with a JDBC connector. And there, for the line item data set, we had a timeout after 20 minutes. So the transfer couldn't finish. But for the others, we also saw something, it's like an order of magnitude difference. And the interesting part here is that Postgres also has its own native foreign data wrappers. So these are kind of built to transfer Postgres data between Postgres instances. And here we also actually perform quite better. So this is also like 2 to 5 times better, which is pretty interesting because, these Postgres foreign data wrappers are really optimized for Postgres instances.
Yeah.
So this was these were some numbers from the end-to-end experiments. And then we also have different, let's say, micro benchmarks, right? So there, for example, we wanted to see like, okay, what is the bottleneck in each in different pipelines? So, for example, when transferring, we have this micro benchmark where we transfer a CSV file to a CSV file, and there, if we increase the read parallelism, it doesn't help, right? Because it's not the bottleneck, it's the deserialization. So there we see, okay, we might need to increase the parallelism degree of the deserializer. But then when we did exactly the same experiment, but we read from Postgres, we saw, okay, actually the read is the bottleneck. So we should increase the read parallelism. And this is again to motivate a little bit why we need an optimizer and why each environment is different. And then I think I just want to share different some for the formats,
Sure.
because there is a conception that columnar format is always better. You should always go columnar. This is not true actually. So we saw that of course when you compress, sometimes because the value domain is more constrained in each column, this may help, but it's not the case for all data sets, right? So here we saw that columnar is not always beneficial as an intermediate format. And also with regard to compression, what is interesting is that the compression library that you should choose also depends on the amount of threads that you will allocate to your compressor and decompressor. So in compression, you have these 3 trade-offs, right? It's compression speed, compression ratio, and decompression speed. And you always kind of trade off those 3 things. And we saw that, for example, in very high-speed networks, compression doesn't help if you don't put enough workers for the compression and decompression. Right. And then for like a low amount of parallelism. So, for example, if you're on a constrained device and you can only allocate a few threads for compression, you might want to choose a different compression algorithm that will give you better end-to-end performance. Even though maybe you may transfer more data because your compression and decompression is slower, you might want to choose a particular compression mechanism, but then this also changes when increasing the threads you allocate to a compressor and decompressor. And maybe one last thing. What we also try to do is to evaluate our cost model. So we compared the we compared the estimated throughputs with the actual throughputs, right, that our optimizer provided. And I mean, they're not perfect, but they work out. They're not too far away from reality. I mean, the estimated ones. And most of the time, we see that it's like overestimated, which is not a problem, because this means that we would, let's say, allocate a bit more threads. We wouldn't have worse performance than expected. So yeah, in that sense, the cost model works fine right now. But as I said, we also have ongoing work on the optimizer, so we hope to be better there as well.
Yeah, to close that gap over time. Yeah, there's some fantastic insights there as well. But I think if we take like a holistic review of all of the results there, I mean, the idea of behind XDBC is I've clearly validated here. Like, this thing definitely works over what we've got else out there in the state of the art. I guess the natural question that sort of follows from this in this discussion is where we've probably touched on quite a lot of bits of where you go next or what's in the pipeline with XDBC coming up. And one sort of topic I wanted to ask you about, and I don't know where this sort of fits into XDBC, is like around fault tolerance, about what happens when data transfers, like things crash, the network's a little bit flaky. Like, how do we handle faults at the moment? Because from personal experience I've seen before, like large data transfers, so the longer they run, the more chance something's going to go wrong. So how do we handle things going wrong, essentially?
Yeah, good question. But I don't have a good answer. This work was more focused on, okay, do we benefit from decomposing the data transfer pipeline? Do we benefit from the different configuration knobs? But of course, we have not addressed different things like, for example, fault tolerance. So on the network side, we rely right now, we have TCP. So if something gets lost in the network, we hope that the TCP, the underlying TCP library will take care of that. There could be more sophisticated things on the fault tolerance side. So for example, having different checkpoints, or like being able to, because right now all this is in memory, right? And if it crashes, forget about it. But we could have something like like a write-ahead log where you could say how much data actually you read from the source and how much of it was written in the target system, so that you can just replay from a particular point in time and not just just restart everything.
Yeah, for sure. The next set of questions, obviously, like kind of impacts and surprises and stuff like that. So kind of jumping off with the impact to start off with, if we've got our crystal ball here, what sort of future impact do you think, or maybe it already has done with XDBC, what impact can it have going long term? Like, what's the long term vision for it, maybe over a longer time horizon? Like, what impact do you think it can have?
Yeah, I think on the one hand, it would be interesting to see if existing data transfer tools like standard XDBC could expose more configuration knobs, right? Because right now, for example, in JDBC, you can just configure fetch size, so how many tuples you fetch from a database. That's it. So I could see different systems exposing more configuration knobs on the one hand. I mean, optimizer in production is always a tricky thing, right? So people don't want too many things to happen automatically. I mean, of course, in a database, you want the query optimizer to pick the best plan for you. But yeah, these machine learning approaches, I'm not sure how much people want to use them in production, because we're talking about the real work now outside the research paper. But yeah, so exposing more configuration knobs for data transfer techniques would be one thing. And then, so there is little interoperability mechanisms between systems. So maybe this work could spark some more initiatives. Obviously Apache Arrow is one such thing, but this is like more like an intermediate format. Of course, there are also things built around it, like, there is the Arrow Flight server, which also kind of provides similar functionality here, but it's also not really, decomposable and configurable. And you always need to go through Arrow. It would be interesting to see how different systems may want to work together. That would be cool. And of course, with the XDBC project, we will try to provide different connectors for different systems so that you can play around and transfer your data fast. But again, like right now, we're just a little team, and this can be seen like you could use it as a prototype, but of course, to go further, this would need more serious work.
Yeah, cool. But I guess on that note, it is a kind of an open source project people can go around and play with, right? If they so choose.
So as we talk, the project is not. So I think that during SIGMOD we will have an open source version that people can play around with. Right now we have code for the experiments, of course, because this was part of the. When you submit the research paper, you always need to be reproducible, and but it's a different thing to expose a framework that's usable, and we have done good progress on that in the last months, and I think that during SIGMOD we will be open source.
Nice, ready for the big reveal. Cool. Yeah. So I guess just we'll go for two more questions here, and the first is surprises. What caught you off guard whilst working on XDBC? What was the most interesting thing that sort of you did not expect that?
Yeah. So interesting for me was that I hadn't done too serious work with C++ before. So for me, it was also an adventure of getting to know the low-level details. And it's crazy how a branch can cut your performance. It's so crazy. But then what was more interesting was that how different systems for different environments you need so much different configurations like this. I didn't expect.
Yeah, that's cool. Yeah, there's a lot of diversity and heterogeneity out there in the wild, right? Yeah, cool. Yeah, so the penultimate one is something that I'm trying out, Harry. So if you've not got anything so that comes to mind, then don't worry about it. But it's giving I don't know whether we did this for Sheet Reader. I think we did it, but for in a DuckDB context. About some sort of recommendation, anything sort of tech related or computer science related, be it a blog post, paper, or tool that you've encountered recently that you thought, oh, that was fun, I enjoyed that, oh, that was cool, go check it out.
Yeah, I think it may sound funny, but Sea Lion. So we often don't appreciate the tooling that we get so much. So yeah, it's very nice. So because we also had very different environment setups and very different, let's say. So we integrated also Python with C++, and then also Java and JNI, and we have different containers running here and there, and it's amazing to see how these tools, in particular, I use and the JetBrains family, let's say, but it was very nice to see how well they work, and what amazing solutions they provide and how much they make our life easier.
Yeah, we take it for granted a little bit, right? And also, C-Line is like a great play on words as well. Like it's a good name, so yeah, it has that going for it as well. So yeah, cool. I guess with that, then let's move on to the last word. Then, so what's the one thing you'd like to get the listener to get from this podcast episode today?
Yeah. So just recapping. So data transfer, I think data transfer is crucial in today's applications, and we actually really focus on making the performance better in each data system, right? But then often we forget about how important integration is, and in particular the interoperability between systems. So I think a lot of performance and resources get wasted on like poor interoperability mechanisms. And yeah, I think XDBC is a step towards making interoperability mechanisms better. But of course, there is more to come.
And we look forward to that. Thanks again, Harry, for coming on the show. It's always a pleasure to have you on. And thanks again. And we'll put links to everything in the show notes as well, listeners. So if you want anything we've mentioned today, you can go and find it there.
Yeah, and I would also like to mention that this is work in collaboration with my colleagues Kaustup Bedkar from the IIT in Delhi and Matthias Böhm at the Bifold Institute in TU Berlin, and of course Volker Makel also from Bifold and TU Berlin.
Cool, great stuff. I guess we'll see you all next time for some more awesome computer science research.
Yeah, thanks for having me, Jack.